We are absolutely living through an AI revolution, right? I mean, you've seen it. It's generating incredible art, it's helping drive cars. The things AI can do are just exploding. But there's something hiding behind all this magic. A massive, hidden cost that we really need to talk about.
So, let's just get right into it. We talk all about how smart AI is, but we almost never talk about its voracious appetite for energy. The very hardware that's making all this possible is putting a serious strain on our power grids and on the planet.
Look, let me just put it plainly. Modern AI has an energy crisis. The way we're building these systems right now is just incredibly inefficient. Training and running these huge models takes a staggering amount of electricity, and their carbon footprint is just getting bigger and bigger.
Okay, so to really get a handle on this, check out this number, 700 watts. That's for just one of these high-end GPUs, the chips that are the workhorses of AI. Now picture a data center. Not one, not 100, but thousands of these things, all fired up 24/7. Yeah, the numbers get pretty wild. A little scary, actually. And this chart? Wow, this just lays it all out. Look at the left. That's your standard GPU, guzzling hundreds of watts. Now look at the right. That's a new kind of chip, a neuromorphic chip. It's doing AI work for a tiny fraction of the power. We're talking orders of magnitude, like a 90–95% drop in energy use. It's insane. So you got to be asking, what is this thing?
Well, it turns out the answer, the blueprint for this incredible efficiency, has been sitting right inside our own heads this whole time. Yep, scientists and engineers are turning to the most sophisticated, most energy-efficient computer known to exist, the human brain.
And this idea isn't brand new. Listen to this from Carver Mead, who's basically the godfather of this whole field. He figured out decades ago that our brains they don't play by the same rules as our computers. They're built differently, and honestly, they're way more effective. Think about it. Your brain does all this incredible stuff on the power of a dimmed light bulb. It's just on another level. And that brings us to the name for this whole approach, neuromorphic computing. And I want to be really clear here. This isn't just about making our current chips a little bit faster or a little more efficient. No way. This is a total rethink. It's a whole new playbook, building hardware that's structured like the brain, with artificial neurons and synapses, processing information in a way that's, brain-like. Okay, so how on earth does this actually work? To get it, we need to dig into the fundamental differences in how these things think. It's really not about what they do, it's all about how they do it.
All right, to really appreciate the solution, you have to understand the problem. Pretty much every computer you've ever used, your laptop, your phone, the biggest supercomputers, they're all built on an idea from the 1940s. The big issue is the brain of the computer, the processor, and its memory are in two different places. So to get anything done, data has to constantly travel back and forth on this tiny digital highway. And that highway gets clogged. It's a massive traffic jam called the von Neumann bottleneck, and it just wastes so much time and energy. Your brain, it's not built like that at all.
And this comparison here really nails the difference. On one side, you've got our traditional computers. They're always on, always crunching numbers, constantly drawing power. But neuromorphic systems, they're event-driven. They basically just chill out, using almost no power until something actually happens. Like a neuron in your brain only fires when it gets a signal. And, this is the big one, they put the memory right next to the processor. Boom, no more traffic jam. So you've got this new kind of hardware, right? Well, it needs a new kind of software to run on it. Instead of the neural networks we're used to, these systems run what are called spiking neural networks, or SNNs. And the cool part is, instead of dealing with a constant stream of numbers, they communicate with these little discrete spikes of information, just like real neurons. It's a way more efficient, way more natural way to handle the kind of messy data you get from the real world. And here's what one of these things actually looks like under the hood. This is a processor called Akida. Now, don't get bogged down by the labels and the jargon. Just look at the overall structure. See that grid? That mesh of interconnected little blocks? Think of each one of those blocks as a little neighborhood of neurons, and each one has its own memory and processing packed right inside. Information just zips between them when it needs to. There's no central highway, no traffic jam. It looks a lot more like a brain, doesn't it?
Okay, so this isn't just some far-off science fiction concept. This stuff is real, and it's already out there solving problems. Let's look at where neuromorphic AI is making a difference, right now, especially in places where every single drop of power counts.
Take all those tiny smart devices everywhere, the so-called Internet of Things. There's a company, Sentient, that makes these tiny chips for voice commands. Hey, device.
The crazy part, they use less than a milliwatt of power. That means you can have a gadget that's always listening, always ready, that can run for months or even years on a single coin battery. It's a complete game changer.
Then you've got autonomous systems, drones, robots, that kind of thing. Because this whole process is decentralized, it's absolutely perfect for something like swarm robotics. You can have a whole fleet of little robots working together, coordinating like a flock of birds, with no single boss robot telling them what to do. Or think about a self-driving car or a drone. This lets them see and react to the world in real time, right there on the device, without having to constantly phone home to a data center. And in healthcare, wow, the potential here is just incredible. People are working on smart prosthetics that can actually give someone a sense of touch by using these brain-inspired sensors. We're seeing it in brain-computer interfaces, and even in things like analyzing X-rays or scans right there on the machine, giving doctors results in seconds, not hours.
So, that's what's happening today. But what's really, really exciting is where this is all headed. Because honestly, fixing the energy crisis, that's just the tip of the iceberg.
This right here, this is the holy grail. See, right now, we train an AI model in a massive data center, and then we basically freeze it and ship it out. It doesn't learn anymore. But neuromorphic hardware, it promises something called on-chip learning. That means the device itself, out in the wild, can keep learning from its experiences, just like our brains do. Imagine a robot that learns a new skill just by watching you, or a health sensor that adapts specifically to your body over time. Your gadgets could get smarter and more personalized for you personally, without ever having to upload your private data to the cloud. That's a huge deal.
Now, let's be real, it's not all smooth sailing. There are some big challenges here. Actually training these spiking neural networks, it's still pretty tricky, way harder than standard AI. We need totally new software and tools. Programmers have to learn a whole new way of doing things. And yeah, we have chips with 1 million artificial neurons, which sounds like a lot until you remember the human brain has around 86 times billion. So we've got a ways to go on the scaling front.
But even with those challenges, the promise is just undeniable. We start off by talking about AI's massive energy problem, right? But what's so cool is that in solving that problem, by looking to our own brains for inspiration, we're doing more than just saving power. We're on the verge of creating a totally new kind of AI, one that's not just powerful, but efficient, adaptive, and able to learn on its own. It's an AI that can finally leave the data center and live out here in the real world, with us. And that leaves us with one pretty big question to chew on.